our final section. Okay, so if you take a positive function between 2 points, say between A and B, and you rotate it about the x-axis. So this is a surface revolution, the kind of yoke you'd make with a lathe. That's not a great drawing. Well, I'm not good at drawing anyway. So some kind of a vase yoke. Put your stuff sideways, you kind of see. So it's a three-dimensional. It's three-dimensional anyway. I hope you can understand what I've drawn there. So like, if you rotated just an ordinary line, you'd end up with a cylinder. Maybe I'll do slightly better drawing of that. Take that, so rotate this around the x-axis at every point. You get a cylinder. If you rotate a line like that, you actually end up with a cone. Yeah, so the thing in the middle is kind of like a big vase, and our job here is to find the volume of it and also to find the center of gravity, which by symmetry will be somewhere along the x-axis. So the volume of the solid is given by integrate pi y squared, and the last task, as I said, is to find the center of gravity. So we'll maybe pick up an easier picture here. So I'll go like, say, here, mirror that. This is kind of like a wine glass with the bottom broken off, right? So it will be along the x-axis. It's not hollow like a wine glass, it's solid. And by symmetry, the y-coordinate will have to be 0. So it turns out that the answer to this question is given by integral of xy squared over integral of y squared. Now it's a bit hard to see the bit down the bottom, but you will have figured out the bottom. So the bottom is the volume divided by pi. Okay, oh yeah, there, that's written there. Okay, so we'll do 2 examples here. What do we got? The area between the curve y equal to the square root of x cubed and x equal to 0 and x equal to 3 is rotated about the x-axis. Draw a rough sketch. So no, I don't know what this yields is. So we're going to just do plot some points. Now where we're going from x equal to 0 to 3, that's handy enough. 0, 1, 2, 3. 0, 1, 2, 3. So we're putting into that formula. Now we can probably, because it's really going to be quite rough, we can probably only really go to 1 decimal place here. So square root of 0 cubed is square root of 0 is 0. Square root of 1 cubed is square root of 1 is 1. Square root of 2 cubed is the square root of 8, which is approximately 2.8. Writing equals 2.8 would not be good there. And then square root of 3 cubed, which is square root of 27, which is approximately 5.2. So we're going to try and plot this. Well, we'll see. So now the other thing is, if you pick a different scale on the x and the y axis, the picture can look a bit off as well, I think. But look, just don't worry about it too much. What you'll be looking for is if your answer really makes no sense, like if it completely falls outside the region, then you'll know you've made a mistake and just say, well, this is obviously wrong, isn't it? And so let's see. So let's go with 1, 2, 3, and let's go with, well, let's maybe do 1, 2, 3, 4, 5, and I'll do the same here. -1, -2, -3, -4, -5. Not perfect at all. And we can plot, if we're rotating it, we can plot above and below. So 0, 0 is the same both ways. 1, 1. 2, 2.8. So 2, 2.8 is around here. 2 minus 2.8 is around here. And finally 3, 5.2 is about up here. 3 minus 5.2 is about here. So it looks kind of like, well, look, whatever it looks like. Kind of looks like a speaker icon on a computer screen. Okay, so hopefully you can kind of see what that is. So by symmetry, we know. Yeah. So the answer, yeah, it could end up being a bit funny yet, just because of the way that. We've done it. The answer mightn't make sense because actually this thing, if you put it in, it's actually far wider than this. Like imagine if you, like, so I'm saying the y-axis, look at this distance, this is 5. But 5 on the x-axis is way longer. So really what you need to do is kind of shrink the x-axis so the shape actually looks a lot more like this if you do them both to scale. And I'm not sure what that will tell you about. So you might get an answer like really close to this, whereas if you put that here, it looks wrong, but it actually isn't. Okay, so don't be too worried about your sketch in that regard. Okay, so that's the first bit, a rough sketch of the solid, that's done. Second thing, find the volume. So the volume is pi times integral of y squared, or the integral of y squared pi, same difference. So we have the volume is, let's say, pi integral. So you go from 0 to 3, and it's y squared. So we got square root x cubed squared. And now obviously that's not in the tables because, well, it's just not like, you need a manipulation. And there's different manipulations you can do here, but really, if you have your head screwed on, you've got square root squared. Squaring is the inverse of square rooting. So we simply get pi times integral from 0 to 3. So the squaring undoes the square root, you're just left with x cubed dx. And now this is something that we can get from the tables because the antiderivative of x cubed is x to the 4 over 4. And now we can do top limit minus bottom limit. So x equal to 3 minus x equal to 0. The x equal to 0 doesn't give you anything. 3 to the 4 is 9 by 9 is 81, so you get 81 over 4 pi. Now if you want, you can approximate that, but I'm not really doing units here, so you can just leave it like that if you want. Now the other thing we need is to find the coordinates of the center of gravity. So what's the formula? It says integral of, you can use whichever one you want. I think we'll use the last one. Integral of pi xy squared. Okay, so we're looking at integral of pi xy squared dx. And we know that we can divide this by the volume, which we know is 81 over 4 pi. Okay, so fix the pi. There's the x and there's the y squared. So let's go through our toolkit. We can't do it directly, so there's a manipulation. So as before, so that integral pi 0 to 3 x pi square root of x cubed squared. So as we just saw, the square undoes the square root. So what you actually got here is x times x cubed. And you can't antidifferentiate these term by term because they're multiplied together. So you need to do further manipulation. This is pi times 0 to 3, x by x cubed. How many x's multiplied together is that? Well, it's 4. And now you're down to something you can handle. So you get antiderivative of x to the 4 is x to the 5 over 5 from 0 to 3. Top limit minus bottom limit pi. 3 to the 5 over 5 minus 0 to the 5 over 5. And 3 to the 5 is something like 243 or something, yeah. So that's 243 pi over 5. Okay, so now we'll use our formula. Where's the formula coming from? Down the bottom, I think we'll use the last one, yeah. So the integral x bar, I should say, is integral of pi xy squared dx over the volume. And the integral of pi xy squared we just found was 243 pi over 5 divided by the volume, which is 81 over 4 pi. And this is certainly one we should go to the calculator with, because we are going to put it in our sketch. So you get 243 by 5 over 243 by pi over 5, all divided by 81 by pi over 4. This turns out to be 2.4. And I will put it in our sketch. And as I was saying, because of it's not to scale, the answer doesn't really seem right. That's where it ends up. Okay, and as I said, it doesn't quite seem right. That doesn't look too bad, but it would make way more sense if everything was to scale. Maybe it does look right. Okay, now in all of these you needed a manipulation to do all the integrals. You could need parts or anything like it. Okay, so let's see this question. Consider the solid generated by rotating the curve y to the e to the x about the x-axis between x equals 0 and 1.5. So usual thing, draw the sketch, find the volume, find the coordinates, indicate on your sketch. So we'll estimate for some points here, maybe just to 1 decimal place. So what's the y? E to the x. So the first one is e to the 0, gives us 1. Then e to the 0.5, approximately 1.6. E to the 1, approximately 2.7. E to the 1.5, approximately 4.5. Now again, we won't go to scale, but we won't worry about it too much either. So we're going 0.5, 1, 1.5, and we're going 1, 2, 3, 4, 5, minus 1, minus 2, minus 3. Didn't work very well there. I think let's start that one again. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And we do the points above and below. So 0, 1. 1, 1.6, something like that. 1, 2.7. 1, 2, nearly 3. And then 1.5, 4.5. Then just the mirror but below. So this looks like it's one of those pint glasses that's really kind of tall. Some German stuff. You know those ones? But again, if we actually drew it to scale, it would look a bit more like a speaker. Okay, but we won't worry too much. We probably should put some of these ticks in. So how about 0.5, 1, 1.5, and maybe we just do 2, 4, minus 2, minus 4. Okay, so that's our sketching. That's okay. Find the volume. So the volume is the integral of pi y squared. So that'll hopefully be written on the next page. So the volume is the integral of, or pi times integral of y squared. So this is pi times integral from 0 to 1.5, and then the y is e to the, was it x? Yeah, squared dx. Now there's a little bit of algebra that kicks in here and there's no real other way of knowing this apart from kind of knowing the algebra of it. If you've got a repeated power, you multiply the powers. Because what I'm getting at is you can't anti-differentiate e to the x there as it is, because it's squared. It's not a sum of terms. It's only when it's a sum of terms. So you go to your manipulation, and the manipulation is that if you have a repeated power, you multiply the powers. And now you're in the table. So what does the table say? The table gives us that the antiderivative of e to the ax dx is equal to 1 over a e to the ax. So we can use that here. So you get pi, and the antiderivative of e to the 2x is 1 over 2 e to the 2x, 0 to 1.5. Top limit minus bottom limit. Now here you have to be careful with that 0, because e to the 0 is 1. So a half e to the 2 times 1.5 minus a half e to the 2 times 0. And as I said, that second term is actually equal to minus a half. So I think we'll put this probably just in terms of 4 significant figures. So pi times half, it looks like e to the 3 minus 1. 29.97, which would round up to 29.98. Okay, so that's the volume of that shape. Now we're asked to find the center of gravity. Have I done something? No, I haven't. Now it's important, by the way, I knew this was a solid, so it's three-dimensional. It could have been a lamina, but it's not. So where's the formula? So we have to do the x-coordinate of the centroid is integral of pi xy squared dx over v. So we need to calculate pi xy squared dx. So this is what we're looking at now. Now, that space isn't going to be good. So we're looking at integral from 0 to 1.5. I should have taken out the pi, but I'll do it in a second. X times y, which is e to the x squared dx. Okay, manipulation. Well, we've seen this manipulation already. E to the x all squared is e to the 2x. So we have pi integral from 0 to 1.5 x times e to the 2x dx. Now you've got x, which is in the tables. You have e to the 2x in the tables, but they're multiplied together. So you can't anti-differentiate term by term, only if it's a sum. So you think about manipulation and there's none other. The only other thing you could do here, or the other thing you could try, is a substitution. But it doesn't work, because the only possible substitution is w is equal to 2x. But you have 2x, but you don't have a multiple of its derivative. And so you'll end up, if you do this, with something like x e to the w maybe over 2, something like that. And when you've got a mix of x's and w's, you've gone wrong. So the substitution just fails. You can try it, but it just fails. And so it's not in the tables because it's multiplied together. There's no more manipulations. Substitution doesn't work, so it has to be integration by parts. So if it's integration by parts, what I would do is I'm going to forget about the limits. I'm just going to work with integral of x e to the 2x dx. If I'm doing integration by parts, I write down the formula for myself. So the formula says the integral of u dv is equal to u v minus integral v du. I have to pick u by Liate. So there's no logs here. There's no inverse trig. Algebraic, yes. Now, the u in integration by parts isn't inside something else. It's multiplying. So in terms of algebraic, which means power of x, this is going to be my u. So u is equal to x, and then everything else is dv. So all that is dv. Okay, So we're going to try and use the formula here. Let's look how space is okay. Sorry there, just make sure we get the space right. Oh, there's loads of space here. Okay, so yeah, we're going to do integration by parts. So let's use the formula. So I, which is this antiderivative x e to the 2x, is u, which is x, times v. Now how do you get v? You get v by integrating dv. So v is the integral of dv, which is the integral of v to the 2x dx. And if we look back up the top of the page, this is in the tables, antiderivative of e to the 2x is 1 over 2 e to the 2x. So that's v. Minus integral v. What's v? Half e to the 2x times du. Now what's du? Well, how you get du is you differentiate u. So differentiate both sides here. Du dx is equal to, what's the derivative of x? 1, and multiply both sides by dx. Du is equal to dx. But you can say if u is x, du is dx. That is, it does work. Okay, and this is okay because now what I might do here is I have x by a half by e to the 2x. It might be easier to write this as a half by x by e to the 2x. And in the antiderivative, I have a half, so I'm going to pull out that half. And then I've left with the antiderivative e to the 2x, which sure I know all about that. Fix my half. What is the antiderivative of e to the 2x? It's a half e to the 2x, and I can multiply the half by the half there if I want, so I get a half x e to the 2x minus a quarter e to the 2x. So we might feel a little bit lost now, but no need. This is where we are, and now we can do that in one line because we have the antiderivative here. Now I think the space for it really is on the next page, but we have plenty of space down the bottom. So if we go back and say, okay, what about pi from integrate from 0 to 1.5 x e to the 2x dx, well, we can say we have anti-differentiated that. It took us a while because it was integration by parts, but we have it now, and we can now do our answer in one line. The antiderivative of x e to the 2x is a half times x times e to the 2x minus a quarter e to the 2x. And we're going from 0 to 1.5, top limit minus bottom limit. The 0 with exponentials, you be careful. So substitute x equal 1.5, so I get a half 1.5 e to the 2 times 1.5 minus a quarter e to the 2 times 1.5. Substitute in the bottom limit. Now the first term will be 0 because it's a half times 0. It doesn't matter what happens after that. But it's minus a quarter e to the 2 times 0, which doesn't give you 0. Now I've got a pi there, but I'm just going to bang all this into the calculator. So pi times, so brackets 1/2 by 1.5 by e to the 3 minus 1/4 by e to the 3. Take away, the first bit is a 0, minus a quarter. So the 2 by 0 is 0, e to the 0 is 1, quarter by 1 is a quarter. So I end up with 32.34. Now where am I? So I'm trying to use a formula which will write on the next page. So I got two numbers there, which I'm just going to pause and record. So the two numbers that we're going to be using, this is the volume, and this is the integral of pi xy squared. So that says we calculate the integral, so we've already done it. So x bar is equal to integral pi xy squared dx over the volume. We just calculated that thing on top to be 32.34, and the volume we found was 29.98. So we'll go to the calculator there. 32.34 divided by 29.98, and we're getting 1.079. And so the center of gravity is 1.079. Now we might forget why is the y coordinate 0, but if we go back and look at our picture, there's complete symmetry about the x-axis, so it has, the center of gravity has to be there. So let's throw it down there. It's about 1.1, so something like that, which again may or may not look correct. So approximately 1.10. That's the center of gravity. All done.